Okay. Stop everything. And ask yourself this. Right now. Why are you still sitting in your chair? Or standing on the floor? You'll say gravity. Of course. But what if I told you that answer is completely wrong? That gravity, as a force, doesn't exist. Not in the way we were all taught. Think about it. We can explain the other forces. Electromagnetism? We found the particle, the photon. The forces inside the atom? We built giant machines to smash particles together and found the gluon, the W and Z bosons. But gravity resists. Completely. For over a century, our greatest minds have hit a wall. There is no graviton particle in any lab. No quantum theory that fits. Nothing. Here's the mental image. Imagine the universe as a still, calm pond. That's empty space. Now drop a heavy ball, that's the sun. It warps the fabric of the pond, creating a dip. Now roll a marble, that's Earth, near the edge of that dip. It spirals in. Not because of some invisible string pulling it, but because the stage itself is curved. That was Einstein's genius. Gravity isn't a tug-of-war. It's geometry. The shape of reality itself. But that revelation opened a door to a much deeper, much weirder mystery. Because if gravity is just geometry, then why does it feel like a force to us? Why does an apple fall? The answer to that question would come from a man who saw the universe not as a pond, but as a swirling, chaotic, probabilistic dance. A man who would look at Einstein's beautiful curved stage, and find the cracks in it. For a while, it seemed like the puzzle was solved. Einstein's vision of curved spacetime was stunning. It predicted black holes, bending starlight, even the Big Bang, before we had proof of any of it. It felt complete. But then, the cracks began to show. And they showed up in the quietest places. In the orbit of Mercury, just a tiny, inexplicable wobble that Newton couldn't explain. In the impossible precision of atomic clocks on fast-moving jets, ticking just slightly out of sync. Einstein's equations worked. Brilliantly. But they worked on a cosmic scale, planets, stars, galaxies. When you tried to bring them down to the quantum realm, to the world of atoms and particles, the math shattered into nonsense. It was like trying to describe the beauty of a symphony using only the rules of grammar. The universe, it seemed, was playing by two separate sets of rules. One rulebook for the very big, gravity, shaped by mass and energy. And a completely different, bizarre rulebook for the very small, the quantum world, where particles are waves, where things can be in two places at once, where reality is fundamentally uncertain. This was the impossible question. How do you stitch those two worlds together? How does the smooth, curving fabric of spacetime emerge from the chaotic, probabilistic foam of the quantum? Einstein spent the last 30 years of his life searching for this unified theory. A single equation to describe everything. He called it his greatest failure. He died believing the two worlds might never be reconciled. That gravity would forever stand apart, a lonely giant, refusing to play with the quantum forces. But in the years after his death, a new kind of thinker emerged. One less concerned with beautiful, singular equations, and more obsessed with a messy, buzzing, infinite sum of possibilities. A physicist who would approach the problem not from the top down, but from the ground up. A man who would ask a dangerously simple question: what if we've been looking at gravity from entirely the wrong angle? Enter Richard Feynman. A mind that didn't just think outside the box, it barely acknowledged the box existed. While others saw a wall between the quantum world and gravity, Feynman saw a playground. His tool? Not a telescope, not a particle accelerator. But a simple, yet infinitely powerful idea, the sum over histories. Now, close your eyes for a second. Imagine a single electron, just one, flying from point A to point B. The old way of thinking said it takes one path. The shortest, fastest route. Like you walking to the fridge. Feynman said, no, he said that electron takes every possible path at once. It goes in a straight line. It also takes a wild detour past the moon. It spins and loops. It zigzags. It does a little dance. All of these paths happen simultaneously. Reality, at its core, is a democratic cacophony of every possible thing that could happen. Our classical world, the one we see, is just the average. The most popular vote in an infinite election of possibilities. This was the birth of quantum field theory. And it worked. It perfectly described electromagnetism and the nuclear forces. It gave us the standard model. So, in the 1960s, Feynman turned this chaotic, democratic machine onto gravity itself. He tried to treat the gravitational field like any other quantum field. He started calculating. He drew his famous diagrams, mapping out how hypothetical gravitons might interact. And then, he hit it. The thing that made even his fearless mind pause. The calculations didn't just get hard. They exploded. They produced infinities, nonsense answers that his mathematical tricks couldn't clean up. It was like trying to calculate the sound of one hand clapping and your calculator screaming infinity back at you. Gravity, it seemed, wasn't just another player in the quantum game. It was the game master. It was changing the rules of the game itself. But in that spectacular failure, Feynman saw something everyone else missed. A hidden clue buried in the mathematical wreckage. An insight so strange, it would force us to rewrite the very question we were asking. The problem wasn't finding gravity's particle. The problem was realizing that gravity might be asking us to look at particles differently. Let's bring this down to earth. Literally. Pick up your phone. Hold it out. And let go. It falls. That's gravity, right? The geometry of space-time, curving beneath it. But now, zoom in. Not to the phone, but to the space between your hand and the floor. On the quantum level, that empty space is not empty. It's a seething, bubbling ocean. Virtual particles flicker in and out of existence. Quantum fields vibrate at every possible frequency. It is, as physicists call it, a foam. Now here's Feynman's hidden insight, the one that changes the picture completely. In his failed calculations, he glimpsed a possibility. What if the falling foam isn't responding to a curve? What if it's creating it? Think of the quantum foam like trillions of invisible springs filling all of space. A completely still, massless object doesn't disturb them much. But your phone has mass. Its atoms are a concentration of energy. And according to quantum theory, energy interacts with this foam. It pushes on those springs. It creates a kind of statistical pressure. Now imagine the phone in that ocean of springs. Beneath it, the springs are compressed more, because they're closer to the mass. Above it, they're less compressed. There's a pressure differential. And what does any object do in a pressure gradient? It moves. It doesn't get pulled. It gets pushed from the region of higher quantum pressure to lower quantum pressure. Down, this is the radical flip. Gravity might not be a force from below, pulling you toward Earth. It might be a pressure from above, from the universe itself, pushing you down into the dent your planet makes in the quantum field. Your falling phone isn't sliding down a slope. It's being statistically herded by an infinite number of quantum interactions. It's the path of least resistance through the noise of reality. This is why Feynman's math broke. He wasn't just calculating a particle exchange. He was trying to calculate the average behavior of everything, all at once. And if that's true, it leads us to the final, mind-bending edge of this idea. The place where not just our intuition breaks down, but our very sense of what is real. So let's follow this to the end of the line. If gravity emerges from the statistical push of the quantum vacuum, then what is it, really? It's not a fundamental ingredient of the universe. It's a side effect. A consequence. A phenomenon. Think of heat. For centuries, people thought heat was a fluid, caloric, that flowed from hot objects to cold ones. It was a thing. Then we understood molecular motion. Heat wasn't a substance, it was the average kinetic energy of molecules. The force of heat was an illusion, emerging from something deeper. Now imagine we're making the same leap with gravity. The force you feel holding you in your chair, the weight of your own body, may be the universe's most convincing magic trick. A collective hallucination woven from countless quantum whispers. This changes everything. First, it dissolves the wall. The great conflict between Einstein's smooth gravity and the chaotic quantum world melts away. Gravity doesn't need to be quantized because it's not its own thing. It's what the quantum world looks like when you zoom all the way out and take the average. The smooth curve of spacetime is the statistical glow of the quantum foam. Second, it rewrites the extremes. Inside a black hole, at the Big Bang, places where our current laws of physics shatter into infinities, we're not seeing a breakdown of gravity. We're seeing the quantum foam screaming. The illusion is peeling back, and the raw, unfiltered machinery of reality is showing through. Finally, it redefines you. You are not a passive object moving on a curved stage. You are an active participant, a concentration of energy constantly engaged in a dynamic, billion-way conversation with the deepest fabric of existence. Your very mass is a standing wave in the quantum fields, and your weight is the echo of that interaction. We began by asking why you don't float away. We end by realizing you are held down not by a force, but by a conversation. A conversation between you and the universe. A conversation where every atom of your body is speaking, and space itself is listening and responding, with a gentle, universal push. The greatest insight isn't an equation. It's a shift in perspective. From a universe of forces, to a universe of relationships. Gravity isn't something the universe does. It's something the universe is. And you are woven right into the weave.